Okie doke. So our look at Euclidean geometry is basically done. But before it's all the way done, I thought it would be wise for us to look at some special points in triangles and how they relate to other special points in triangles. And so I am going to draw, if that's okay. Let's draw a triangle. So here's some line segment. We'll call that AB. And we'll draw a segment up to C. And then we'll draw a segment back to A. So this is just a generic triangle. And because this is dynamic geometry software, we can move that triangle around and all the side lengths change. So it's just some generic triangle. What I'd like to do first is I'd like to construct the midpoint of this side right here. So midpoint right there, we're going to call that D. And what I'll do is construct the median from C down to D. The median is drawn from a vertex to the midpoint of the opposite side. And then I'll do that over here also. I'll construct the midpoint, some point called E. And then I'll take the segment from A to E. It is no surprise that these two medians cross. It is no surprise at all. I'm going to call that point G. No surprise at all. What is surprising is that if I draw a ray, that's not going to work. Let's do it this way. If I construct the midpoint over here, some point that we will now call F, and I take the segment from B to F, oh, guess what? That point is the point of concurrency for all three medians. This thing is called the centroid. The centroid of a triangle is the point of concurrency for all three medians. And you can tell that if I just move this around like so, no matter what size the triangle is, those three medians will come together at one point called the centroid. But it gets better. If I were to take the segment from C to G and then the segment from D to G, and I were to measure them, if I were to let's do them one at a time. If I were to measure them, that's about 3.31-ish. That's about 1.66-ish. Take a look at the ratio between those two. Yeah, it's about 2 to 1. And it's about 2 to 1 no matter where I put the triangle. And there's nothing special about picking vertex C. I could have done this from any of the vertices. And so we see, at least in a not quite rigorous way, but we at least see in an intuitive way that the centroid divides a median into a 2 to 1 ratio. Well, while I'm on the topic, I just want a new, there. Take a triangle, a generic triangle, and instead of drawing medians, let's draw altitudes. Let's construct a perpendicular. There's the foot. And we'll take the perpendicular from A to BC. No surprise that those should cross. We expect that. We expect that these two lines will cross. Oh, come on. That's right. We expect that these two lines will cross at some point. What is surprising is when we take the third altitude, it also goes through D. All three altitudes go through D. D is referred to as the orthocenter of the triangle. The orthocenter, that's the place where the altitudes are concurrent. And that will be true no matter what kind of triangle we, oh, the orthocenter. The orthocenter could be on the triangle. Notice what kind of triangle this is if that happens. And the orthocenter could be inside the triangle. Notice what kind of triangles do that. And the orthocenter could be outside the triangle. Notice what kind of triangle ABC has to be to force the orthocenter outside. Very interesting development. But wait, there's more. Take a generic triangle. And instead of medians or altitudes, let's just take perpendicular bisectors. Let's take, let's construct a midpoint, and then from that midpoint, construct a perpendicular line. Ooh, it's almost an equilateral triangle. Great, we'll do it like that. Then on this segment, we'll construct a midpoint, and given that midpoint and that line segment, we'll draw a perpendicular line. No surprise that those things should cross. No surprise that this perpendicular bisector and this perpendicular bisector cross. That's not a surprise. What is surprising is that if we do the same thing on this segment, that it also goes through F. Point F is called the circumcenter of the triangle. And it's called the circumcenter of the triangle because if I construct a circle centered at the circumcenter with radius distance from the circumcenter to any of the vertices, it goes through the other two vertices. The circumcenter is the center of the circle that circumscribes the triangle. And that is true no matter how I jiggy this around like so. Note, if the triangle is that's an interesting kind of triangle. The circumcenter is on the circle. And then if I want the circumcenter to be outside the triangle, look what kind of triangle you need to do that. So just some things to observe to help you remember some geometry and some trigonometry that you may or may not have studied when you were in high school. Now, the curious thing is that the circumcenter and the orthocenter and the centroid, well, you'll have to wait till you come to class tomorrow to learn something very, very interesting about those special points. So that's what I need you to know. And I need you to be somewhat familiar with this kind of software because I think I'd like to do a little bit of playing with this when we gather next time. Okay, so that's a bit on centroids and orthocenters and circumcenters, and I'll see you next time.